All right, today we're going to pull back the curtain on one of the planet's biggest secrets, a hidden engine that's been quietly controlling Earth's climate for, well, forever. And this story, it's not written in the sky or the oceans. Nope, it's written in stone. So let's get into it.
Okay, so here's the big question, right? For literally billions of years, through everything, asteroid strikes, massive volcanoes, even as the sun's brightness has changed, Earth has somehow managed to stay, well, livable. How is that possible? What's the secret? Well, you might be surprised to hear it all comes down to the incredibly slow life and death of rocks.
So, where do we even start? Our journey begins with something that's happening right now, all around us, every single day. But it's usually way too slow to even notice. And that is, simply, rocks breaking down. Now, this isn't just about a landslide or something. This is the very first step in a massive global chemical story.
Right, so the official name for this is weathering. Pretty straightforward. You can think of it as this constant, relentless attack by the elements, wind, water, ice, on the solid surface of our planet. And believe it or not, this simple process is the starting point for everything we're about to talk about, how the rock cycle actually influences our air.
And weathering really comes in two main flavors. Over on the left, you've got physical weathering. Just think of that as nature's hammer. Smashing big rocks into little ones. Simple. But what we're really interested in is over on the right, chemical weathering. This is where things get fascinating. It's where the actual chemistry of the rock gets changed. And that is the key to this whole climate puzzle.
Okay, so how does this chemical reaction actually happen? We're diving a little deeper now, moving from just breaking rocks apart to the invisible, but super powerful chemical reactions that literally connect solid rock to the air we're all breathing.
This is really the heart of it. It all starts with rain. Seriously. As raindrops fall through the sky, they pick up a little bit of carbon dioxide from the atmosphere. This creates a really weak acid called carbonic acid. Now, when that slightly acidic rainwater hits certain rocks, specifically silicate rocks, which by the way make up most of the Earth's crust, it starts to slowly dissolve them. And here's the magic trick. During that reaction, the CO2 that was a gas floating in the air gets trapped. It's converted into something called bicarbonate ions, which are now just dissolved in the water. It's basically a natural, planet-sized CO2 scrubber.
But that captured carbon doesn't just vanish, right? It's now starting this epic, slow-motion journey. It gets carried by rivers and streams all the way from the mountains down to the ocean. And this is where we have to totally shift our sense of time. We're not talking days or years anymore. We're talking geological time. And check this out. Once those dissolved bits and pieces finally make it to the ocean, they can hang around for an unbelievably long time. I mean, look at this. Aluminum, iron, they're in there for over 100 years. Not bad. But then you get to rubidium. 270 million years. What this shows us is that the whole process that started with a raindrop, well, its payoff happens on a timescale that's just immense.
All right, so all these minerals have washed into the sea. You'd probably think, okay, story's over. It's all just a big mineral soup now. But you'd be wrong. Something totally wild, almost counterintuitive, starts to happen on the ocean floor. Rocks start to be born all over again.
And yeah, they actually call this reverse weathering, which is a perfect name because it's exactly what it sounds like. Instead of rocks breaking down, all those dissolved ingredients in the seawater start to clump together. They form brand new clay minerals right there on the bottom of the ocean. The fancy science term is marine clay mineral authogenesis, but reverse weathering really hits the nail on the head.
And we're not just talking about generic mud either. These are some really cool and specific minerals, things like autunite, glauconite, selatonite. These are called authogenic clays, which is just a way of saying they are formed in that spot. They're just silently crystallizing down there in the dark, and as they do, they are completely changing the chemistry of the ocean around them.
Okay, time to connect the dots. We've got rocks breaking down on land, weathering, and we've got new rocks forming in the sea, reverse weathering. It's the way these two processes play off each other. That is the secret sauce. That's Earth's climate thermostat.
So here it is, the whole planetary balancing act in one place. On one side, you have silicate weathering on land. That process sucks CO2 out of the atmosphere, which over very long timescales cools the planet down. But on the other side, you have reverse weathering on the seafloor, and that acts as the counterbalance. So here's how the thermostat actually works. If the planet starts to get too hot, chemical weathering on land speeds up, pulling more CO2 out of the air, and that cools things back down. But if the planet gets too cold,
weathering slows down. That lets CO2 from volcanoes gradually build up in the atmosphere, warming things up again. It's this absolutely brilliant self-regulating feedback loop that has kept Earth in that just right zone for life for billions of years.
So, all of this ancient geology brings us to a really cool modern idea. If this natural process is so good at pulling CO2 out of the air, what if we could speed it up? What if we could sort of hack the rock cycle to help us with our current climate situation?
And yeah, that's exactly what scientists are exploring right now. There's this thing called enhanced rock weathering, or ERW. The idea is to just grind up a bunch of the right kind of rock and spread it on farm fields to dramatically speed up those CO2 capturing reactions. Other big ideas include ocean alkalinity enhancement, which is all about helping the ocean safely absorb more carbon. And even these minerals themselves, like glauconite, are being looked at as amazing, slow-release fertilizers for more sustainable farming. It's pretty incredible. We're learning to team up with Earth's oldest systems to solve some of our newest problems.
It's pretty mind-blowing when you think about it, isn't it? Our whole journey started with a single raindrop hitting a rock on a mountain, and it ended with new crystals forming in the deep sea. This ancient, incredibly slow but powerful cycle has kept our planet stable for eons. And now, it turns out that understanding it might just be the key to protecting our future. The big question is, can we learn to work with these massive geological forces wisely?